So we know that with a real battery, we have an internal resistance and the EMF, and we attach a load over here. So this is our battery right there. Okay. Plus into the battery, minus in the battery. Okay. So the question is, what is the maximum power getting to the load over here? I want to know what's the maximum power that we get to the load. And you say, well, we know that the power dissipated in the load is I squared R. Okay, so we want to make something really big here. Okay, the bigger I is, then the bigger the power. The bigger the R is, the bigger the power. And so we say, well, wait a minute. What about we try two things? Okay, so if in order to make I big, then we make R small. Right? So the ultimate limit is R going close to 0. Well, if R goes to 0, the current does not become infinite. Now, if there's no internal resistance, the current becomes infinite, right? And so if R goes to 0, current goes infinite, so infinity squared times 0 is going to be like infinity. So you're going to get an enormous amount of power. But in a real situation, you have that internal resistance. So that means that even if RL goes to 0, then the total R is going to be R, and so the current just goes to E over R. Okay, well, that's not 0, so something not 0 squared times 0 is going to be 0, so that means the power would go to 0. Okay, so obviously RL going to 0 is not going to be the solution. So our other extreme is, how about if RL goes to infinity? Well, that's not going to work either, because if RL goes to infinity, then that means the current, which is over R, is going to go to 0. Well, 0 squared times infinity, you know, L'Hopital's rule wins here, okay? Power goes to 0. So if the load resistor is too big or the load resistor is too small, we actually get less power dissipated. So what you have to have is the load resistor just right. This is like a Goldilocks principle. Can't be too small, can't be too big. It has to be just right. And so what we want to do here is figure out what would that be. We go back and we say power equals I squared R. And I want to maximize that. Okay. Now, how do we maximize that? Well, we need to know that I is the EMF over R plus R. So that means the power is going to be EMF squared R divided by R plus R squared. And I want to maximize that. So how do you maximize a function? We take a derivative and set it equal to 0 and see what you get. So to maximize that, I want to find out what R I need. So I take the derivative with respect to R of the power, okay, and set that equal to 0. So this is the derivative with respect to R of EMF squared R over R plus R squared. And I want to set that equal to 0. So the EMF squared comes out, and I want to take a derivative with respect to R of R over R plus R squared, set that equal to 0. Well, I can divide through by that, both sides by that, and it doesn't change. So I just need to get this equal to 0. So I got to do that derivative. Well, it's a quotient. So we know how the quotient rule works, right? Okay, so it's the derivative of the top times the bottom minus the bottom times the, it's the derivative of the top times the bottom minus the derivative of the bottom times the top divided by the bottom squared. So that would be dr is just 1. So it's 1 times r plus r squared minus 2r plus r times r divided by r plus r to the 4th, and that's going to have to equal to 0. Well, I can cross multiply by that and get rid of that, so it means that r plus the numerator has to equal 0. Well, let me factor all that out. So that's going to be equal to r squared plus 2rr plus big R squared minus 2rr minus 2r squared equals 0. So those two cancel, and I get r squared minus big R squared equals 0. So in other words, r squared equals r squared. Or, yeah, that means r equals r. So that means that if I want this situation right here, internal resistance, EMF, R, the load resistance, if I want this to have the maximum power dissipated in the load, then those two must be matched. So we have to match those. Now, this is the interesting thing, that you just match that, you get the maximum power out here. Okay. So think about dry cells. You've got like a big flashlight battery here, that's a D cell. You have the smaller ones that are C cells. You have the much smaller ones that are the AAs, and then you got the little skinny ones, which are the triple A's, and then there's actually some really tiny ones that are quadruple A's. Well, what's the voltage on them? Well, the triple A's are 1.5 volts. Well, it turns out the double A's are 1.5 volts. The quadruple A's are 1.5 volts. The C cells are 1.5 volts. The D cells are 1.5 volts. They're all 1.5 volts. So why are they not interchangeable? Why can you not just stick a D cell into something that uses double A's? Well, for one thing, it wouldn't fit. But the other reason is the big difference between these is they have different internal resistances. The way I've drawn it is R is bigger that way and R is smaller that way. So that means these have smaller internal resistance than these. Okay, so what you do is, whatever you're trying to power, it's got a resistance of its own, and you want to match the resistance of your device to the resistance of your battery in order to get the maximum power to it. So if you have a flashlight and you got the bulb in the flashlight, different flashlight bulbs are going to have different resistances. Okay, so that's why different flashlights, some of them use D cells, some use C cells, some use double A's, and some use triple A's. You would match this up to what you need it to be. And so that's the whole point behind that. And so internal resistance is an application of that.